All right, so the domain of a function of two variables, it's understood as the set of all ordered pairs for which the function is defined, unless otherwise stated. Sometimes we're going to restrict the domain and we'll state that. Otherwise, it's just everything that makes sense to plug into the function. And so a lot of the standard rules of domain apply. So really nothing too shocking here for this part. The first example, you can see that, okay, square root has to have something positive, but the inside is always positive. And so here, the domain of f is everything. It's all of R2. So instead of saying the domain is all reals, we're going to say the domain is all of R2. You can plug in any ordered pair that you want. So here, for the second example, we realize that, okay, for the domain of this guy, I've got to have y minus x greater than or equal to 0, so y greater than or equal to x. And so the domain of G is the set of all pairs x, y in 2 space such that the y coordinate is greater than or equal to the x coordinate. And sometimes it's kind of helpful to visualize these, so you can actually graph sets like this. So let's do that together just so you can see how this works. So what you typically do is you want to graph, even if this was a strictly greater than, if it was just greater than, you'd still graph the equals of these kinds of restrictions. So I'm going to do that. Let's do that in purple. I'm going to graph the equals. If it was strictly greater than, I'd do a dotted graph, but it's actually equal, so we'll do that. So here is that. And now I want the y-coordinate to be greater than or equal to my x-coordinate. So that means I'm going to actually shade. Let me pick a size here that I can work with. I'm going to shade the top half of this graph. Oops. And then, well, yeah, I'm not trying not to line up the shadows here. Let's start over. Can't bear to not have that look right. Okay, so we'll do something like that. And then there we go. So even though I can't draw it all because there's actually no boundary this direction, the domain goes on and on and on. As long as you're above that line, y equals x, we'll stop there. So I want to switch to Mathematica with you and actually graph some examples for fun. Usually I ask students to make up things, but since you're not here, it's kind of hard to do that. But let's switch to Mathematica and have a look. All right, I wanted to show you a couple of fun plots. We're going to just plot some 3D functions. So here we're plotting z equals sine of x squared minus y squared. And you can get a sense of what it looks like. Mathematica struggles with some of these, but it does a pretty good job. So you can actually see the parabola y equals x squared sort of playing out here. And then the sine, of course, is rippling it. So that's a fun surface. I graphed another one for you. This is just z equals sine of x plus y. And you just get the sine wave, but it's at an angle now. So there's, if you look at it from this perspective, you can see the classic Calc 1 sine wave. But of course, we can see it this way as this rolling wave here. So if you were imagining trying to model something, say ocean waves, then this would be a nice way to do that. So that's another surface. Another surface I've got is sine x, z equals sine x plus sine y. You get this kind of almost like an egg carton. I've seen clouds that if you're looking up at the cloud, it looks a little bit like that. That's kind of fun. Here I've got a little more complicated one. This is a rational function. And you can sort of see you've got, it's almost like we dropped a little rock here and we have a little stick poking up there. But you can just do all kinds of interesting surfaces, which are useful for modeling all sorts of things in many different fields. I wanted to do one where there was something undefined, and so you can see that this z equals this expression is undefined along the line y equals x. So you can actually see, looking down on the plane y equals x, you can sort of see that rift here where the surface isn't defined there, but it kind of goes to minus infinity on this side and z equals plus infinity on this side. So those are just some examples that I hope are helpful to you, and we'll go back to the iPad screen now. Okay, so I wanted to do one more example with you before we go on, and that's just to help illustrate that some of the equations that you've seen, like this plane, you should recognize this is a plane. I can read off the normal vector is 1, 2, 3, so on and so forth. But you can actually, if you want to, solve for z. You can, let's actually say this, you can solve for z, and when you do, you get what? go ahead and work that out yourself just to make sure your algebra skills are good. You get z is 1/3 2 minus x minus 2y. And so the point is you can view this plane as f of x, y, a function of two variables, equals 1/3 2 minus x minus 2y. Not a huge deal, but sometimes it's really helpful to be able to solve for one variable. By the way, you could solve for x and view x as a function of y and z, or vice versa. We typically solve for z, though. All right, so that's it for this video. In the next video, we're going to talk about level curves, and these are basically just traces sliced a certain way.